Modern recommendation systems are built upon three fundamental pillars that allow them to predict user intent with high precision. Collaborative filtering identifies patterns by comparing users. If user A and user B share a common interest in an item, the system assumes they share a similar taste profile. Content-based filtering focuses on item metadata. By analyzing attributes like genre or theme, the system matches products directly to a user's known preferences. Hybrid models combine these strategies, integrating real-time context like time and location. This allows systems to be dynamic, adapting to the user's immediate state and environment. The recommendation pipeline starts with retrieval. This initial step is designed for extreme efficiency, narrowing down millions of potential items to a few hundred relevant candidates using fast search techniques. By utilizing approximate nearest neighbor searches, the system quickly discards irrelevant data, ensuring the process remains performant even with massive scale. This phase prioritizes speed and broad coverage. Once the initial candidates are identified, they are passed along for more intensive processing in the ranking stage. The final stage of the recommendation pipeline is re-ranking. After retrieval and ranking, we have a list of candidates, but they may be too similar, leading to a filter bubble. During re-ranking, the system applies business logic. It adjusts the order to ensure diversity, prioritizes fresh content, and injects serendipitous items to broaden user discovery. Items pass through this layer to be reordered. By intentionally mixing content, we ensure the user is not trapped in an echo chamber, keeping the experience engaging and varied. This re-ranking stage transforms a raw list of scores into a curated, meaningful, and balanced feed, tailored to the user's long-term satisfaction. Recommendation systems have evolved from static lists into complex generative reasoning engines. Traditional models simply rank items based on past clicks. Modern systems now perform multi-step reasoning. They don't just output an item, they generate a narrative explanation for why it matches your current intent. By integrating large language models, the engine maps your semantic intent to specific item attributes, providing a transparent, natural language justification for every choice. This transition turns the recommendation engine from a black box into a collaborative partner that understands the context behind your decisions. Large language models have fundamentally changed how recommendation systems function, moving them beyond simple keyword matching to deep semantic understanding. While traditional systems rely on static tags and matching keywords, LLMs interpret the underlying meaning of a user's search and their current context. By identifying if a user is in learning mode or entertainment mode, the system adjusts the recommendation strategy to align with the user's immediate goals. Graph neural networks, or GNNs, revolutionize recommendation systems by mapping complex relationships as a web, rather than a rigid table. Traditional models treat data as static tables. GNNs instead view users and items as nodes in a graph, connected by edges that represent interactions. By allowing information to flow between nodes, GNNs uncover hidden patterns, like a user's indirect affinity for an item through a mutual connection. This enables systems to identify deep, multi-hop patterns that traditional statistical models often fail to detect. Modern recommendation systems transform items into high-dimensional vectors. Think of these as coordinates in a vast mathematical space, where items with similar meanings are positioned close together. Semantic search works by finding items near a query point. Instead of matching exact keywords, it identifies items that share conceptual relationships. When searching through billions of items, we use approximate nearest neighbor, or ANN, algorithms. These allow systems to retrieve relevant results in milliseconds by partitioning the vector space. Traditionally, recommendation systems were built to maximize click-through rate. This metric measures the immediate probability that a user will click on an item. While effective for driving immediate engagement, optimizing strictly for clicks often leads to the promotion of clickbait and sensationalist content that fails to provide real value. Modern systems are shifting their objectives. Instead of just tracking clicks, they now prioritize long-term user satisfaction and time well spent. By measuring post-consumption sentiment and retention, these models create a healthier ecosystem that keeps users coming back, not because of a fleeting reaction, but because they genuinely value the content. This evolution marks a pivot from treating users as simple click generators to understanding their long-term intent and well-being. Traditionally, recommendation systems relied on centralized cloud servers. This approach often faced challenges with network latency and growing concerns regarding the privacy of user data. Modern systems are shifting toward on-device or edge personalization. By moving the recommendation computation directly to the user's hardware, companies significantly reduce latency and keep sensitive preference data entirely local. Edge AI ensures that personal habits remain within the device, providing a private and highly responsive experience. This architecture represents the future of secure, intent-driven recommendation engines. Historically, many recommendation systems operated as black boxes. Their internal logic was opaque, making it difficult for users or developers to understand exactly why a specific recommendation was made. However, increasing regulatory pressure, such as the EU AI Act, now mandates transparency. Organizations are required to move beyond these opaque models to ensure users understand the reasoning behind AI-driven decisions. Explainable AI, or XAI, acts as a bridge. By providing explicit, human-readable explanations, such as listing the specific preferences or item attributes that triggered a recommendation, these systems rebuild trust. This transparency is no longer optional. It is a fundamental requirement for modern, safe, and ethical AI deployment in recommendation engines. One of the biggest challenges in recommendation systems is the cold start problem, where new users arrive without any historical interaction data for the system to analyze. Zero-shot discovery solves this by using cross-domain knowledge. The system identifies semantic patterns in a category where the user has shown interest, such as books, and maps them to preferences in a new category like movies. By leveraging vector space representations, the model recognizes that a specific genre of literature shares underlying thematic structures with a corresponding film genre, enabling accurate recommendations without needing a single click in the target domain. This breakthrough ensures that even with zero history, the system can provide personalized discovery, effectively bridging the gap between past interests and future preferences. Recommendation systems are often too good at narrowing focus, creating a filter bubble that leads to homogenized taste. To combat this, engineers utilize a technique called the serendipity injection. This process involves intentionally introducing 5 to 10% of content that lies outside of the user's typical profile. By doing this, the system breaks the feedback loop and fosters organic discovery. The result is an expanded interest horizon, preventing boredom and ensuring the user remains curious. This intentional injection is vital for maintaining a dynamic and healthy recommendation ecosystem. Historically, platforms used topical matching. If a user watched a cooking video, the system simply recommended another video about cooking. Now, large language models analyze semantic intent. The system understands if a user is in learning mode or entertainment mode to tailor recommendations. This allows platforms like YouTube and TikTok to predict not just what you might like, but why you are engaging at this specific moment. Traditionally, e-commerce relied on keyword matching and static filters. Amazon's Rufus AI changes this by acting as a conversational agent, capable of processing multiple user constraints at once. Rufus analyzes these trade-offs, balancing durability against price constraints, while understanding the contextual requirement for cold weather performance. Spotify's AI DJ illustrates a masterclass in modern recommendation architecture. It moves beyond static lists to create a living music experience. The system synthesizes two primary data streams. First, deep collaborative filtering that builds a rich, long-term musical taste profile. Second, it integrates a real-time feedback loop. This captures immediate user sentiment, whether you skip a track or listen to the end, to adjust the flow instantly. The AI DJ acts as the synthesis engine, blending history with intent to generate a truly dynamic, personalized stream of music. Recommendation systems gather preference data through two primary channels. Explicit feedback involves direct user input, while implicit feedback is derived from natural user behavior. Explicit feedback is highly accurate but limited in volume. Users rarely rate every item they interact with, creating a sparse data environment. Implicit feedback captures the vast majority of interactions. By measuring dwell time and consumption patterns, systems reliably infer preferences without requiring manual user input. Modern predictive models favor these implicit signals. They provide a continuous, real-time data stream that reflects true intent far better than occasional ratings. As of mid-2026, the landscape of digital discovery has fundamentally shifted. Over 80% of all content consumed on major streaming and retail platforms is now driven directly by algorithmic recommendation systems. This statistic highlights that recommendations are no longer a side feature, but the primary engine behind modern digital engagement, effectively curating the majority of what users see and interact with daily. We are witnessing a fundamental shift in recommendation systems. We are moving away from delivering static, rigid lists toward becoming fluid, interactive partners. In the future, the system no longer simply retrieves items. It acts as an agent that understands your evolving goals in real time. This dynamic personalization treats the user as an agent with intent. As your context shifts, the system recalibrates its reasoning engine, adapting its suggestions to match your immediate shifting requirements. Ultimately, the recommendation system of the future is not a destination for clicks, but an interactive partner helping you navigate your choices. Our journey through recommendation systems reveals a clear trajectory. We began in the era of basic statistics, relying on simple collaborative filtering. We then evolved into the era of context, where graph networks and real-time signals allowed systems to understand the why behind user behavior. Finally, we have entered the age of generative reasoning. Here, systems act as intelligent agents that can reason about intent and provide personalized, explainable discoveries. We have transitioned from matrix-based statistics to generative agents, marking a fundamental shift in how we interact with technology to find what we love.